Human evolution never stopped. It just got harder to notice. No generation wakes up with gills or night vision. Instead, one inherited variant edges upward in frequency because its carriers leave slightly more surviving children. Then another does the same. Thousands of years later, ordinary people can drink milk as adults, live where thin air should wreck them, or hold their breath long enough to worry a lifeguard. Some of these shifts are recent enough that the carriers are alive right now. One population has spleens built for diving. Another carries an ancient DNA fragment that stops high-altitude blood from thickening dangerously. Some humans have lost molecular doors parasites once used to get in. Others carry defenses that block infection while quietly raising the risk of kidney failure, autoimmune disease, or a severe blood disorder. And today, selection may be shaping traits nobody would put in a comic book. Reproductive timing, metabolism, how well a body handles its own diet.
The strange part isn't that we're evolving, it's what counts as a win. Evolution doesn't chase stronger or smarter humans. It has no picture of the future. It reshapes populations only when inherited differences change who has children and how many. A gene that keeps you healthy to 90 but stops you having kids is a dead end. A gene that causes trouble at 60 but helps you reproduce at 20 can spread fast. Natural selection plans about as far ahead as a distracted teenager. No one evolves within their own lifetime. Train at altitude and you'll make more red blood cells, but that's change within one body, not evolution, which needs inherited variation shifting across generations. No single population does that in lockstep. A gene that helps in Tibet might be useless in Manila. Human evolution isn't one highway toward a finished human. It's millions of small, local negotiations. One clear story starts with milk. Every infant makes lactase, the enzyme splitting lactose into absorbable sugars. In most mammals, and historically most humans, lactase production falls after weaning, since an adult rarely has access to another species' fridge. Drinking milk after that just feeds lactose to gut bacteria, which respond with gas, cramps, and a fast reconsideration of your choices. But once some groups began herding cattle, sheep, goats, and camels, milk became a dense source of water, calories, fat, protein, and minerals, and mutations near the lactase gene emerged that kept it switched on into adulthood, not just once. Separate lactase persistence variants evolved independently across Europe, East Africa, and the Middle East. Same problem, different fixes. This is evolution moving through culture. Domestication reshaped the environment, and the new environment made certain genes valuable. Europe's variant spread fast, though not simply because people drank more milk. Dairying predates lactase persistence by a long stretch, and many groups processed milk into cheese or yogurt to strip the lactose out. Researchers now suspect the real advantage showed up during famine or disease, when dehydration from drinking unprocessed milk could turn deadly rather than just uncomfortable. In plenty of populations today, low adult lactase remains the norm. The person drinking a latte with zero consequences is biologically the unusual one. Milk is simple next to the Tibetan plateau. At high altitude, every breath delivers less oxygen. A lowlander compensates by making more red blood cells. Useful until it isn't. Push it too far and blood turns thick, the heart strains, and the risks of clots, stroke, and chronic mountain sickness climb. Pregnancy gets especially dangerous, since a fetus depends on oxygen crossing the placenta. Tibetans facing this pressure for generations didn't evolve to overproduce blood cells. They evolved to not overreact in the first place. Many carry variants near EPAS1, a gene tied to the body's low oxygen response, keeping hemoglobin comparatively modest at altitude. The strange part is where that variant came from. Tens of thousands of years ago, ancestors of some modern humans interbred with Denisovans, an archaic human group related to Neanderthals, and a Denisovan-like EPAS1 version stuck around in Tibetans because selection favored it. Genetic hardware inherited secondhand from another kind of human. Populations in the Andes and Ethiopian highlands solved the same problem differently. Same mountain, different answers. Environments don't demand one correct response, just enough workable ones.
If altitude reshaped blood, the ocean may have reshaped an organ. The Bajau are traditionally seafaring people across Indonesia, Malaysia, and the Philippines, who dive and forage underwater on repeated breath holds with minimal gear. Compared to a nearby non-diving population, Bajau spleens ran about 50% larger on average. The spleen isn't just storage. Mid-dive, it contracts and dumps oxygen-rich blood cells into circulation, the trick marine mammals use at a larger scale. This could look like training, except non-diving Bajau also had enlarged spleens, pointing to something inherited rather than built through practice. Genetic analysis flagged selection near PDE10A, possibly acting through thyroid pathways. Compelling, though the sample was limited. Calling the Bajau aquatic humans oversells it, but their spleens show how fast a way of life can become a biological pressure. Food has been just as inventive a sculptor. Salivary amylase starts breaking down starch in the mouth, why a plain cracker slowly tastes sweeter the longer it sits there. The AMY1 gene encodes it, and people carry different numbers of copies. Populations with long histories of starch-heavy diets tend to average more, though the timeline is messy, since cooking made starch important long before farming existed. Fat metabolism shows a similar pattern. FADS gene variants affect how the body processes fat, and Greenlandic Inuit populations show strong selection tied to a marine diet. An adaptation tuned to one food environment behaves differently once surrounded by refined carbs and processed food. Evolution tunes bodies to yesterday's menu. Globalization changes the menu faster than genes can keep up. Disease produces even stranger traits because pathogens fight back. Malaria has been one of the most powerful forces in recent human evolution. The parasite invades red blood cells, so evolution has repeatedly reshaped those cells' surface proteins, or the hemoglobin inside them. The best-known case is sickle cell, a variant in HBB. One copy gives strong protection against severe malaria. 2 copies can cause sickle cell disease, where cells distort, block vessels, and shorten life. The variant swings between protective and devastating, depending on whether it appears once or twice. And evolution never resolved that. It just kept it running. Because where malaria killed many children, carriers of one copy survived and reproduced more often than carriers of none. Other defenses hit different targets. The Duffy protein is an entry point for Plasmodium vivax, and a mutation that switches off Duffy expression became extremely common across sub-Saharan Africa. Don't reinforce the door, remove the handle. But the parasite adapts too. Vivax infections do turn up in Duffy-negative people, suggesting some found alternate routes in. Trypanosomes struck a different bargain. A POL1 variants, found mainly in people with recent African ancestry, can kill the parasites behind sleeping sickness, but 2 high-risk copies sharply raise kidney disease risk. Good in one setting, costly in another. Pandemics leave similar echoes. During the Black Death, plague wiped out a massive share of Europe's population, and ancient DNA points to strong selection near URAP2, an immune gene whose protective version likely helped carriers survive, shifting gene frequencies within a handful of generations. But an overzealous immune system is its own danger. Those same variants are linked today to higher risk of inflammatory conditions like Crohn's disease. An immune system built for an era when failing to attack meant death by Thursday sometimes attacks now on days that never called for that intensity. This reveals the real pattern. Selection rarely hands out a free upgrade. It shifts risk around. More clotting stops bleeding and causes clots. More inflammation fights infection and attacks the body. A trait survives only when its benefit outweighs its cost locally. And then humans change the locality through medicine, migration, and diet. None of this ends evolution, it rewrites the pressures. Take childbirth.
The pelvis has to allow efficient walking while passing a baby with a large head, an awkward compromise by design. C-sections let mothers survive obstructed labor that would once have been fatal, and some researchers have floated that this could ease selection against narrow pelvises, slowly raising the rate of difficult births. Plausible, but thin evidence, since C-section rates are driven mostly by hospital access and policy, not genes. This is exactly where evolving right now claims go astray. A trait can spread without evolution touching it. Height can rise from better nutrition. Puberty can arrive earlier with more available energy. Nearsightedness can spike from more time indoors. None of that proves gene frequencies moved at all. Even the famous extra artery deserves caution. The median artery normally fades before birth, but in some adults it persists, and one study found it far more common in people born in the late 20th century than the 19th. Headlines ran with "Humans are growing a new artery," but a rising frequency alone doesn't reveal a cause. Genetics, maternal health, or sampling bias could all play a role. It's a fascinating trend, not proof of an upgrade, and not purely a bonus anyway, since it can also compress a nerve and contribute to carpal tunnel symptoms. The hardest traits to study are polygenic ones, shaped by thousands of variants at once. Height, fertility, disease risk, behavior. Some modern studies find evidence that selection is acting on reproductive timing today, and records from a French-Canadian island population even suggested a genetic shift toward earlier first reproduction across roughly 140 years. But reading modern selection is genuinely hard. A gene linked to education might affect fertility only indirectly, through income or family planning, and those environments can shift within one generation. A statistical link between a polygenic score and number of children doesn't mean evolution favors intelligence or any headline-friendly trait. Genes shape environments, environments shape reproduction, and the causal arrow ends up buried under several others. What can be said with confidence is simpler. As long as inherited differences affect who reproduces, humans keep evolving. Medicine now lets people with once fatal genetic conditions survive and have children, relaxing certain kinds of selection without ending it. New pressures keep arriving. Novel pathogens, delayed reproduction, shifting diets, urban density, heat. Climate change may eventually favor heat-tolerant or water-efficient variants, but predicting winners is nearly impossible, since medicine and migration move the goalposts faster than adaptation can spread. Culture now evolves faster than anatomy, maybe the defining human trait. We don't wait for fur before moving into cold climates. We make clothing. We don't wait for stronger jaws. We cook. We don't wait for resistance to every infection. We build vaccines and sanitation. Technology buffers and redirects natural selection. But underneath that armor, genes keep running their slow arithmetic. One family leaves slightly more descendants. One variant edges upward. A population migrates. A pathogen shifts shape. An ancient defense becomes a modern disease risk. There's probably no single future human waiting at the end of this. Populations are mixing more than ever, blurring regional differences while introducing fresh variation elsewhere. Genetic engineering may eventually make some changes deliberate, but edited inheritance is design, not the blind process that produced lactase persistence or altitude adaptation. The humans evolving right now aren't prototypes for a superior model. They're proof evolution works with whatever problem happens to be expensive at the time. Extracting nutrition from milk for herders, carrying oxygen without thickened blood for Tibetan highlanders, stretching the gap between breaths for Bajau divers, surviving one threat even when the defense created another for communities facing malaria or plague. For modern humans, the strongest pressure right now might not even be visible yet. A new infection, a shift in reproductive patterns, a changing climate deciding which inherited differences suddenly matter. The trait might already exist, quietly, as a rare variant in someone alive today. Nothing about that person will glow. They may never know. But if their descendants consistently survive or reproduce better under tomorrow's conditions, that variant spreads. Centuries from now, scientists might pinpoint the moment selection began and call it an adaptation. We'd have just called it a weird family trait. That's what human evolution looks like while it's happening. Not a march toward perfection, not a species inching toward telepathy, just adults who can drink milk. Mountain populations with blood that knows when to stop. Divers carrying extra oxygen in oversized spleens. Immune systems still fighting wars declared by our ancestors. Every trait is a compromise. Every one solved a local problem. And somewhere in the human population right now, another strange solution has probably already started. Evolution just hasn't told us which one yet.